Everyone, I'm Won Lee. I'm going to explain standardization in regression model. We have studied the standardized variable, normal distribution, and the use of standardizing for any values, any variables. Actually, I talk about talk about this standardization in regression analysis. What kind of a result we obtain, we can get it. In regression analysis, there are occasions when variables need to be standardized. The estimated coefficient values of each explanatory variable are interpreted based on the unit of data, right? Every variable has unit. So by comparing beta I hat, this is in bold, but it is estimate, beta I hat, okay? Comparing beta I hat values, we cannot determine how much more one explanatory variable influences y compared to another explanatory variable. Furthermore, if we want to understand how many times more one explanatory variable affects y than another. Okay, this is necessary to standardize the explanatory variables. The method for standardizing data is the same as what we learned earlier. Specifically, the model in which y and the explanatory variables x are standardized as follows. Y can be standardized. Okay, you may imagine the data like this. This is a small sample data. There is y bar, and there is standard deviation of y, these values. So yi minus y bar divided by sy, then standardized for x. Also, x1 can be standardized. Mean of x1 subtract divided by s1 is a standard deviation of x1. x2 also standardized, xp standardized. Then the parameters will be changed, maybe different value. So beta 1 star, beta 2 star, beta p star plus epsilon I star. Each beta I star is also called beta coefficient. This terminology is, I think, very famous in social sciences field. Let us look at the result obtained from the model with standardized values. It's a simple example. For example, let's consider sales y, variable y, unit 1,000 are explained by purchasing cost x1, unit 100, and number of visiting customers x2, unit 10 persons. So I collect this kind of data. Actually, this is 9,000, right? This is 20,000, 22,000, something like that. This one, x1 unit is 100, 400, 800, 900. This one is 40 person, 100 person customer, 80 customers, right? Okay. The model is yi equal to beta 0 plus beta 1 xi1 plus beta 2 xi2 plus epsilon I. The standardized model will be yi star equal to beta 1 star xi1 star. Beta 1 star xi1 star is here. Beta 2 star xi2 star. I2 star is like this. Okay? Of course, y star is here. Epsilon I star. The asterisk star indicates the standardized variables, and beta 1 star, beta 2 star are the coefficient of standardized explanatory variables, with the value of beta 0 star being 0. This is always 0. Okay, beta 0 star. So I don't include beta 0 star here. Okay, let's see the result of computation. Okay, here is a statistical package provides this result, OLS, ordinary least square. Okay, this OLS is not important terminology. So where this one is for original your data. Intercept minus 0.65, x1 1.55, x2 1.76, and the p-value here 0.829, 0.047, here 0.097. Okay, these are p-values for this parameter. This you can test this one, this result. R square is 0.901. You can see that increase of 1 unit purchasing cost, 1 unit purchasing cost, this one, X1, result in an increase of 1,550. This unit is 1,000. So 1 unit means 100 increase in purchasing cost, then you get increase of 1,550 in sales. And the increase of 10, this one X2 unit 10 customers coming leads to an increase of 760 in sales, increase 760. However, with the coefficient obtained above, we cannot determine which explanatory variable, x1 or x2, has a greater impact on increasing sales. Why? Which one is greater, more important? Okay, which variable is more important? We cannot compare the value of these two estimates. So, in order to know which one is important or greater impact on Y, we use standardized regression model like this. The model is actually here, but result like this. So that result from second table here, okay, intercept minus 2.359 times what? E minus 16 power. It's all 0, right? You don't worry about it. Beta 0 star, beta 0 star hat. It is always 0. X1, standardized one, 0.4982. 4982. The p-value is just the same. The properties does not change. I mean, property of x1 does not change. The same p-value here. And 0.4373 beta 1 star hat, p-value 0.097, same p-value here. From this result, we can determine how much more important the purchasing cost x1 are compared to number of customers, visiting customers. How much more they contribute to increasing sales. Okay? From this ratio 0.4982 divided by 4.4373 is 1.25. So this one is bigger, right? 1.25. Purchasing cost x1 can be seen to have an effect of increasing sales by about 25% more compared to the number of visiting customers. You understand this interpretation? Okay. This one is x1 is say is more important than number of customers, visiting customers. How much? 25% much. Okay. Or that you may use in real data this kind of a standardization model. Okay, that's it today. Thank you.